Okay, let's go ahead and kick things off. So thank you so much for joining us today. Again, the title of today's webinar is Indoor 3D Modeling, Applications and Implications. We're really excited to have everyone here today. Before we get started, we just wanted to acknowledge the difficult times that we're all living through right now. For those of you who might be feeling the pain, we just want to say that our thoughts are with you. And our thoughts are certainly with all of the folks doing essential jobs right now. So these are certainly strange times that we're all living through, and we just wanted to take a moment to say that here at the beginning. So that being said, let's go ahead and proceed with the webinar. We're really excited about what we have to share with you today. So I'll be your host. My name's Zach Dukowitz. I'm the Content Marketing Manager here at Flyability. And today we'll be hearing from Andrew McIntyre, who's a technical trainer and mapping expert at Pix4D. We'll also be hearing from our head of marketing here at Flyability, Marc. A few housekeeping items before we get started. The first is when you look at your dashboard in GoToWebinar, you'll see a caret that points to questions. It's the Q&A pane. If you open that, you can type in questions at any point during the webinar. And you can see in this short video we have. So we encourage you to type your questions in here. Unfortunately, due to the size of attendance, we can't have people asking questions live through the audio. It would just be chaos. But we really do want to hear from you. So at any point during the webinar, if you have questions, please type them in. We'll be doing our best to answer questions live as they come in writing. We'll also be compiling questions for the Q&A that we have at the end of the webinar. And on that note, here's the agenda for today. So you'll see at the bottom, we actually have a lot of time devoted to the Q&A. And again, just to emphasize, we really want to be answering your questions, providing as much value as we can for everyone who's taken the time to attend today. So just to go through the agenda real quick, we'll start with a 5-minute introduction. That's what we're doing right now. I'll hand things off to Marc. Marc will speak for 15 minutes on the topic of why use photogrammetry to build 3D models of indoor spaces. Andrew will take things over from Marc. Andrew's going to talk about key considerations when capturing images of an indoor environment. And then again, we'll have 20 minutes devoted to the Q&A here at the end. So without further ado, I'd like to introduce Marc, our head of marketing. So just a few words about Marc. Marc works closely with customers. He has a genuine interest in what they're doing and a curiosity for their needs and the solutions that can meet them. Marc brings a decade of experience to his work as Flyability as an engineer and marketer in semiconductors and embedded electronics applied to the security and aeronautic industries. Marc's been with Flyability since the early days of the company. He's really helped build up the marketing team. And today he's going to share different photogrammetry applications being used in the indoor drone community. So without further ado, I'm going to go ahead and hand things off to Marc.
All right. Good. So glad you're all here today. We've passed 300 people watching this webinar live, which is really cool. And as Zach introduced, so I'm going to take you through the reason why somebody would want to start doing photogrammetry of indoor spaces in order to build 3D models. As probably some of you know, about a year ago we released the Alias 2, and with this new technology in the field, we started to be able to build a 3D model of indoor spaces. And when I'm talking about 3D model of indoor spaces, I'm talking about, spaces which have inaccessible places inside. So like this chimney that you see on my screen, which has very high places and very difficult to reach height. So without a drone, that was impossible to build such 3D model before the release of Alias 2. Of course, indoor 3D modeling is a fairly new domain of activity, and we learn a lot through our clients, and the examples and the applications I'm going to take you through today are drawn from real cases that come from our clients, and some are real cases and some are expectations or applications that they're targeting in a near future. Well, you'll see that through those applications, there's many similarities with outdoor application, but the way you capture the data is quite different. And Andrew is going to talk extensively about that right after my presentation. So why someone would want to do model of indoor spaces? One of the first reason is actually to organize data. What you have to remember is that when you're flying indoor, there is no GPS signal. So it's extremely difficult to geolocalize your data or to even have a relative position of your data, or at least with the technology that we're presenting today, which is the Helios-2. The other aspect, very important to keep in mind, is that when you're usually reviewing your data once the mission is finished. It's not necessarily on the field that you're actually treating the data. You sometimes have to review the data after the mission. And if you have not been diligent enough to mark on a blueprint everything that you see while you're performing the inspection, it can sometimes be very difficult to organize your data and to visualize where this data is located. I can take this example. Here is a huge boiler that contains about 200 of these burners that we see on the screen. So I don't know if I can draw anything, but here we see one of these burner that I'm just circled. There are 200 of these, and you know, sometimes you have to inspect all of them to see if they're in good shape. And there's nothing more that looks more similar to this burner than the one that is next to it. So a 3D model in that case really helps to organize your data and understand which one has defects and which one should be repaired or be considered by further investigation. Another use case, you know, is when you're inspecting the roof of a tank. As you can see here, there is beams, and on a roof tank there is probably 20 to 30 beams, and there is nothing that looks more like a beam than another beam. And again, the same problem arises. How do you differentiate between two beams, and how do you mark and organize your data? So this is really one of the most important application that we see, and the first one I wanted to present today. The next one is making measurements. So this is really something where we see a lot of value as well through the eyes of our customers. The image that you see on the right, it's an elevator shaft. And in this place, you have many things that are inside. You have cables, you have you know, cross beams, you have many elements that are cluttering the space, and it's very difficult to get a complete measurement of the entire shaft if you're using traditional methods. So here, a 3D model, or on a 3D model, so this is really an example, but on a 3D model, obstacles that are in the way of traditional means to make measurements are no longer obstacles, because here you look at the 3D model and you can cross things completely. So suddenly you can measure things that were not previously possible without this this technology. Another example here, we're looking at the top of a chimney where the refractory is missing. And here we were able to measure the area for our clients of missing refractory. And this is extremely useful in the planning of maintenance to know how much refractory they will have to apply, and also at which height this refractory is missing. And speaking about refractory, this is another example which took place in a refinery, and this is the central pipe of an FCC unit where there was missing refractory. And by looking at the feeder stream, it was very difficult to assess if there was anything to be done for repair. And by building a 3D model, it was a very good helper to make the decision whether or not further maintenance was required. A last example of measurements. Here you see stockpiles that are happening indoor, and this is also one client, and they have to regularly assess the quantity of material they've been accumulating, how much they've been removing, and it's indoors, so it's extremely hard to make a model. And here it's quite a wide area where they're stocking these stockpiles, but they have silos and they have more narrow spaces where even bringing standard equipment on a tripod is very difficult. So they've seen a lot of value in using the Helios-2 to build those 3D models. Another application which is quite interesting is checking the shape and the condition of structure. Here on this picture, we see the Helios-2 inspecting rocks. So this takes place inside a stope in an underground mine. So for those who don't know what a stope is, it's a huge cavity where the ore is extracted to be then refined and transformed into valuable material. So here we were filming with another Helios-2 because there is 100 meters of void below the Helios-2 that you see on the image. And the end goal here was to create this model that we can see here, which would not be possible to be built otherwise than with a drone, because entering that space is extremely dangerous. At any time, you can have a rock the size of a car falling from the ceiling on your head. So it's definitely a place that you don't want to enter, and it's actually forbidden to enter. But what's interesting on this model to see, it's here, what you see on this image here, it's very difficult to see here, but there is what we call overbreak. So overbreak is exceeding material that fell into the cavity, and which is diluting the ore that is extracted by the miners. And this is actually changing the quality of the material. And without a 3D model, it's quite hard to see how much overbreak is happening, and if there is overbreaks happening. Another important aspect of this model that you can see is here at the top, the gallery where they've been drilling and to create the first blast. The gallery is not straight. It's actually deviating from the original plan. So this is also something which is very very interesting that you can actually see on 3D model is how much you're deviating from your original plan. Let me go ahead and erase those things that I've drawn on the slide. Sorry for that. Okay, and another application that is quite as interesting as well is blueprints. Is my blueprint still accurate? Through maintenance and repair, it can lead to physical changes that are never reported on blueprint, and those changes can be significant. So it's by building a 3D model, you can actually compare that to the original blueprint, and you can see what has changed through time. So you can track changes. And sometimes, blueprints just don't exist, so you want to go ahead and build the first version of the blueprint. And in a similar fashion, we have a client that is building very large piece of equipment, and of course they have blueprints, initial blueprints that they build the model after, but the as-built machine or the final product that they're building sometimes differs from the original plan. So they want to provide accurate as-built blueprint to their clients. So they're using photogrammetry to do that, and they're exploring the use of Helios-2 because there are very tight space in these machines that they have to explore to build the entire plan. And the last aspect, which is very interesting with photogrammetry, is the planning of maintenance and design changes. So one aspect is staging the assets that that you're going to inspect. So, when you're asking yourself, which technology can I actually use to inspect that space, or how high should I build scaffolding, or is there any places where I can hang the scaffolding and be efficient, or saving costs, not scaffolding the entire place. So all those things, this is something you can simulate in your 3D model. Another aspect is, when you have to move large pieces of equipment through a given space, can you actually do it? Is there enough space to move this equipment through the space? This is something that using 3D model, you'll be able to assess as well. So that's it for the applications, and a few words as a conclusion. So keep in mind that drones are only a tool in your toolbox. They're not a magic solution that does everything. Sometimes other technology will be helpful to build 3D models, or photogrammetry might not be the right solution, but at least what we see from our clients and from our users is that photogrammetry and Ilios2 can really help a lot in many cases. Keep in mind also that these applications are in their infancy, and we don't know yet everything about them, but it looks very promising, and we'll make sure to keep you updated with everything that we learn along the way through our social media and everything that we can use to communicate with you guys. And definitely what we've learned is that photogrammetry is not going to replace standard inspection. It's a complementary tool which comes on top of using video stream to do your inspection. But they're really here to help you locate your data, make measurements, which are definitely the most valuable applications that we see for the moment. And also 3D modeling is definitely a first step. We all dream about running AI-powered classification algorithm on 3D data sets to identify, characterize, or localize elements in the model. And this is ultimately what will make the most sense in the industry we serve. A last word on flyability. If you're interested to start using or getting trained on using Ilios2 to build 3D model using photogrammetry, we have a training course that you can learn more about at flyability.com/indoor-photogrammetry-training. We're working on to make this training available online to face the current sanitary crisis. If you're interested, just go ahead and check out this webpage. Thank you very much for your time, and on to you, Zach.
I'm really excited to introduce Andrew. Andrew McIntyre is a technical trainer and mapping expert at Pix4D. He's hosted classes around the world on how to use Pix4D software. In addition to his experience teaching people about best practices when it comes to Pix4D solutions, Andrew has lots of experience providing technical support for a wide range of applications. Today, Andrew is going to be highlighting some of the most crucial things to think about when capturing images in an indoor environment for the purpose of 3D modeling. And he's especially going to be highlighting 3 specific things to consider when using photogrammetry to build 3D models of indoor spaces. So, Andrew, I'm going to go ahead and hand it off to you.
Too cool. Awesome. Thank you, Zach. I trust by now that people can hear me and hopefully see me as well. Otherwise, I think the chat would be blowing up. So here we go. Now, in the next few minutes, because I don't have, unfortunately, an unlimited amount of time, I'm going to talk about 3 sets of considerations that I think everyone should take into account when they're planning to create a 3D model of an interior space. So to be clear, there are more things that I anticipate most, if not all of you, will have to take into account. So please remember that the next 2 slides do not cover everything I think you need to know about collecting data for an indoor environment. However, I hope this will be a good starting point for most of you, so you can get started with a basic understanding of what to do. Now, first things first, I want to make sure that we all have a very basic, I can't emphasize that enough, it's incredibly basic, understanding of how multi-ray photogrammetry works. So in the 2 examples, you can see that the position of a single point in 3D space has been computed. In the graphic on the left, the point's position is represented by the red ellipsoid. In the graphic on the right, the point's position is represented by the green ellipsoid. As you can see, the volume of space where that point can exist is smaller than in the graphic on the left than it is in the graphic, no, excuse me, other way around. It's smaller in the one on the right than it is on the left. Generally speaking, the more images you have that capture the same thing from different perspectives, the more complete and accurate your results will be. So to compute where that single point exists in space, we must have three pieces of information. Number one is the camera's internal parameters, which defines how the path that light travels is changed when it interacts with the camera's sensor sensor and lens. Right? The camera's external parameters, which define the position and the orientation of the camera when it captured each image. And then lastly, where in the overlapping images the same thing is. Now, how you obtain that information depends on the image processing workflow you're using, which unfortunately I do not have time to discuss today in detail. However, if you provide the image processing software with enough information, the software can compute that information for you, which is why now I want to talk about three different things that I recommend you take into consideration when you are collecting your data. First things first, lighting. So unfortunately, indoor spaces typically contain significantly less light than outdoor spaces, but it may not be immediately obvious because the human eye can account for dramatically different amounts of light. Cameras can also account for differences in lighting conditions by modifying the exposure settings, which include the aperture of the lens, the speed of the shutter, and the sensitivity of the sensor, which is more commonly referred to as the ISO. However, the human brain is great at filtering out or ignoring what our eyes see when what you see with your own eyes is blurry. Cameras, on the other hand, will continue to capture images even if the images are blurry, because the exposure settings cannot account for the lighting conditions and the speed of the camera as it moves around the project area. So one way to increase the chances that all of your images are crisp and clearly represent the project area is to consider illuminating the scene. Thankfully, the Helios 2 has taken care of some of that for you by including lights on the drone that are pointed in multiple directions to illuminate where the camera is pointing. In an ideal world, the light source that illuminates the indoor space would not move as you were capturing your images. However, the lights on the Helios 2 are a reasonable solution because many, if not most of you, cannot access the space that you're trying to reconstruct and install additional light sources. If you choose to artificially illuminate the space, the lights should emit a diffuse light so that the lighting conditions throughout the entire project area are as consistent as possible. And you should not capture the light sources in the images because it can cause the rest of the image to be underexposed or too dark. Right? If you are working with the lights on the Helios 2, which I anticipate most, if not all of you are, you should find a reasonable balance between the camera's exposure settings, or the EV value, which you can change with the controller, and the distance between the Helios 2 and the object. If you capture images closer to the surface, you will have more light to work with. However, you have to balance that with the fact that as the camera moves closer to the object, the field of view of the camera will become smaller, which means that you will then have to capture more images to achieve the same amount of image overlap. And you also increase the chances that you disturb dust and other debris in the project area, which can then introduce errors into your reconstruction because now there's moving objects in your images. So by now, you may have noticed that I have not mentioned a specific brand or model of light, a specific set of exposure settings, a specific distance between the Helios 2 and the object you want to reconstruct, or a specific speed at which the camera should move around the space. That's simply because there is no single recommendation I can make that is appropriate for everyone here today. Therefore, the next time you capture images of an indoor space, I suggest that you consider capturing just a few test images that mimic the lighting conditions, your camera's exposure settings, and the speed of the camera to see if you can clearly identify the objects you want to reconstruct. If you can't, then because the images are too blurry or too dark, you can increase the amount of light that reflects off the surfaces of what you want to reconstruct, either by adding more lights or by simply flying closer to the object with the Helios 2. You can also consider flying slower or changing the camera's exposure settings, or a combination of those three things. Now that we have a basic understanding, of how to illuminate an indoor space, I want to talk about how you can move your camera around the project area. Now, I trust you'll remember that just a few minutes ago, I mentioned that multi-ray photogrammetry relies on the image processing software, or U&I, to identify the same thing in images that capture the object, the surface, or the feature of interest from different perspectives. So to ensure that you have the information you need, I want to talk about how you can position and orient your camera. So key number one, always, and I cannot stress this enough, always try to capture a smooth transition from one image to the next. So for example, Pix4D Mapper relies on the content in the photos to compute your camera's internal and external parameters, and then also create a 3D reconstruction of your project area. If the perspective of the camera changes abruptly from one image to the next, Pix4D Mapper will have a much more difficult time trying to tie your images together. A common instance where an abrupt change in perspective can negatively impact a project is when there is a sharp corner in the space. So instead of capturing images right up to the edge of one surface and changing the orientation of the camera and then continuing to capture your images, you should continue to capture images as you reorient the camera to transition from one part of the indoor space to another. One other benefit of capturing a smoother transition from one image to the next is that it reduces the chances that you abruptly change the direction of the camera, the camera is facing by yawing or rotating the direction the drone is pointing around the Z axis. So drones can yaw very quickly, and that yawing can cause your images to be blurry. So by slowing down the rotation of the drone along the Z axis, not only do you have a better chance of tying your images together, but it also reduces the chances that your images are blurry. Key number two, never capture more than one image at the same position. Images provide valuable information when they capture the same thing from different perspectives. So if you place the camera in the center of the project area and rotate the camera 360 degrees, which I admit is very tempting, all of the images will capture the same thing from the same perspective. And the 3D reconstruction will either have a significant amount of noise if the software is able to generate anything with the images at all. Therefore, always capture images from a different position in space. Key number three, whenever possible, please try to capture the same thing from a consistent distance with your camera. Objects can be represented differently in images if the images were captured at different distances from the object. And therefore, both the software and you and I are ultimately relying on the pixels in the images to compute the geometry of the objects. So if the same thing looks dramatically different in different images because the images were captured at a different distance from the object, that inconsistency can then introduce more errors into your reconstruction. Key number four, as I mentioned before, so that includes the image processing software and you and I, must be able to identify the same thing in different images that were captured from different perspectives to reconstruct the project area. So you may have been wondering, what is the appropriate amount of image overlap, or how many images must I capture for each feature of interest or object that I want to reconstruct? Unfortunately, there is no single number that applies to everyone because there are a number of variables that determine the optimal number of images to capture, including things like the heterogeneity of the image content or the texture, how complex the geometry of the object is, and the accuracy you want or you need to achieve to get the job done. The last one is also how much time you're willing simply to dedicate to the project. However, as a starting point, I believe that capturing everything in at least seven images is a reasonable starting point. That's in part based on my own experience and also thanks to the experience of other team members at Pix4D. So some of you may have already gotten the job done with less image content, and if that's true, then I'm happy for you and keep it up, right? However, if you are just getting started or you find that your results are inconsistent or inaccurate, one of the best ways to tackle the problem is to simply capture more images. Please note that considering that the Helios 2 captures video, that it is possible for you to actually have too many images. Because if you were to extract every single frame from the video, you would have numerous images that were captured at practically the exact same position. Therefore, you need to find a reasonable balance between capturing enough images, but not so many that you are not, if you are not already satisfied with the results that you're getting. Key number 5, as tempting as it may be, Please plan to capture the images so the camera is moving perpendicularly to the direction that the camera is facing. Another way to say it is that the camera should move from side to side instead of forward and backward. And I recognize that it may not be possible to always move the camera perfectly sideways due to logistical constraints, but that ideally is what you would aim for and consider any other type of movement a compromise. Right? Now, another way of summarizing everything that I've just said, and something that I also will use when trying to capture images of an indoor space, is to treat my camera like a can of spray paint. If you've ever read the label on a can of spray paint, it will say something like, spray from a consistent distance with even overlapping strokes back and forth across the object that you want to paint. The same kind of logic can be applied. The difference is that instead of literally painting the object, you're painting the object metaphorically with the pixels that your camera captures. Okay? Unfortunately, pixels alone are not enough, however, to scale and orient a reconstruction. So we have one more thing to consider. Under normal circumstances, Pix4D Mapper, along with other image processing software, typically relies on either the image geotags or ground control points, or a combination of the two, to compute the scale, the orientation, and the position of your reconstruction. However, when you're reconstructing an indoor space, you are significantly less likely to have the ability to capture either of those types of information. Thankfully, if you know the length of at least one thing, and you can identify a handful of objects that are either perfectly, or at least close to perfectly, oriented so that they are perfectly vertical or horizontal, then you can use those objects to scale and orient the reconstruction in a relative space, kind of an arbitrarily defined environment. So in this case, you won't be able to identify the absolute position of something on the face of the earth, but you will still be able to measure the size of something or distances within the context of your reconstruction. Now, if the space is inaccessible, other way around. If the space is accessible, right, you can consider entering the space and either measuring the dimensions of a handful of objects that you will be able to clearly identify in your photos, or you can even place objects like photogrammetric targets or spray painted X's, for example, at different distances relative to each other, so you have an easier time identifying the points in your images later on. However, for the sake of today, let's assume that the indoor space is not accessible. In that case, you can rely on design diagrams, as-built diagrams, your own knowledge of the project area, or a combination of those three things to determine the scale of a handful of objects and the orientation of them as well, which you can then use to scale and orient the rest of your reconstruction. Now, whenever you are including scale and orientation constraints, one best practice is to use constraints that are as long as possible. The longer the constraints are, the less of a chance you will introduce a systematic error across the entire reconstruction. There is, unfortunately, no single length for a constraint that is appropriate for everyone, because the appropriate length of a constraint depends on a number of variables, including the size of the project area, the accessibility of the project area, how accurate your results must be to get the job done, just to name a few. Now, let's imagine that your constraints are relatively small compared to the size of the project area. One way to account for that is to include multiple constraints that are distributed throughout the indoor space. By adding multiple constraints and identifying them in different groups of images, Pix4D Mapper can compute a more reliable result by taking all of the constraints into account. So while a single scale constraint and a single orientation constraint is enough to get started, I personally try to always include at least 2 scale constraints and 2 orientation constraints. In the end, the total number of constraints you will include in your project will ultimately be up to you to decide based on your circumstances. Now, if you choose to include multiple constraints, please distribute them throughout the entire project area so that you can mark them in as wide a range of images as possible. Marking multiple constraints in a limited number of photos that are all clustered near each other doesn't have as much of an impact on ensuring that your reconstruction is correctly scaled and oriented compared to distributing the constraints throughout, because then you're able to mark the constraints in a greater number of photos. Now, time permitting, I'd like to quickly demonstrate how to add a constraint in Pix4D Mapper desktop, but I also know that the question and answer session is coming up really quick. So Marc or Zach, if either of you would let me know if you think we have time. It takes about 3 minutes.
You're just fine, Andrew. Yeah. Please proceed. You're
Cool.
Just fine.
Let's do it. All right, now, for those of you who are following along, you are welcome to also open a project if you can do it quickly enough and try to do the same thing. Now, in this example, that some of you actually saw Marc showed in the presentation earlier. Now you can see it in 3D, and I hope that the screen is not lagging too much. Okay. Now, for the sake of today, I'm going to add just one manual tie point. Oops, I need to get back into that inside the environment and find that manual tie point that I had just been looking at before, which is right here. Okay. Now, for the sake of today, let's just imagine that I can clearly identify the distance between these 2 points. The first point is near this spray painted target that you can see here, and I'm going to use the center of it. Now, once I've found that object, or that feature, in at least 2 of my images, and for those of you who didn't know, a little trick to open up all of the images in kind of like full screen is you place your cursor in the image, and then you tap the space bar on your keyboard. I'll zoom out, try to find it again. Okay, tap the space bar, and now, ready to go. Uh-oh, my screen resolution's acting up today. There it is. Okay, now that I found the same thing, and I admit that this actual feature is a little bit too big relative to the ground sampling distance, considering that I have so many pixels that represent that dot. Ideally, it would be smaller, but that's what I'll use today. Okay? I then click New Manual Tie Point, and then I mark that feature in a handful of photos. After I mark 2, I can click Focus on Selection just here, and it will then update the framing in all of my other images, and then I can mark additional photos if I need to. And I should always be able to clearly identify where that feature is. Now, for the sake of time today, I'm just going to imagine that I've marked this manual tie point in a sufficient number of photos. And I don't have time to talk about how you determine what is a sufficient number of photos in the context of this webinar today. Okay? So I'll save that result by clicking Apply here. And then the software will show me in 3D space where that point exists. And you can see this manual tie point now exists here in the 3D environment. Now, if I knew the distance between that point and one other point, I could then add a scale constraint to scale my entire reconstruction. Now, I've already taken the opportunity to mark 2 manual tie points, which you can see here on the opposite side of the stope. One's here on the right side of my screen, and the other one here is here on the left. And to make it a little bit easier for you to see what I'm actually working with, I'm going to quickly hide that first manual tie point that I just made, and then I'm going to clip the point cloud so you can now see kind of a cross section of the stope, whereas before it was a full 3D reconstruction. Now I've kind of cut the thing in half, and half of the points that represent the stope are now hidden from view, so I can see the inside more easily. Now I click New Scale Constraint, which is here in the top left corner in the Create toolbar. I place my cursor on the object and I click once. I then move over to, excuse me, the second point here, and I always place my cursor on the biggest part of the manual tie point, and then I right click to add the last vertex and finish the creation of that scale constraint. Now in this example, we're imagining that I actually have a known distance between those 2 points. And I could have gotten that from a design diagram, I could have gotten it from an as-built diagram, or we could have measured it on site using either a tape measure, if it had been accessible, or any other type of tool that allows me to measure a distance in an environment where GPS signals are denied. Right? Now, Pix4D Mapper believes that this dimension right now is 16.22 meters. For the sake of today, I'm going to imagine that I know that that dimension is actually, let's say, for the sake of today, it's actually 23.5 meters based on whatever information I have elsewhere. When I click Apply, you'll see that the numbers are still different, but you can see now the software has computed the difference here. It's about 7 meters difference. So clearly, my reconstruction is too small based on the information that I have. If I had more scale constraints, I would do the same process multiple times. And then after I've added the constraints to my project, for the software to take them into account, I would go to Process and then Reoptimize. Now, some of you may be wondering, what does that mean? As you can imagine, once again, I don't have time to talk about the differences today between Reoptimize and the other processes in Pix4D Mapper desktop. But by doing that, Pix4D Mapper will then take into account the new information I've just added and then scale, in this case, our project up by that scale factor. And it applies in all directions. So just because I have one scale constraint doesn't mean it applies in one dimension. It will apply in all 3 dimensions evenly. And ideally, I would have more constraints, but of course, we only have time to do one today. Okay. Now, that's all I have to say today. Of course, if there are any questions that I can answer during the question and answer session, then I'll be happy to try.
Wonderful. Thanks so very much, Andrew. That was really thorough and really helpful, I think, for a lot of folks on, just judging by what we're seeing in the chat pane and the Q&A pane. There are definitely questions. Before we dive into those questions, I just want to let everyone know that a recording of this webinar will be going out to everyone who signed up. So you can look for that in your inbox. And if you need to go back over what Andrew just covered, especially there at the end, obviously you can peruse that at your leisure once you get the recording. A few other things before we get to the Q&A. We are doing a webinar series right now. What we're doing is sharing content we originally planned for our in-person user conference. Of course, due to the ongoing pandemic, we had to cancel. So we've moved all of that content online into this webinar format. We've already done 2 webinars. Today's the 3rd. The first 2 you can see at the top of the screen here on API and ASME standards as related to drones and inspections. The second one was with DJI on country of origin drone bans and how they might impact US companies and US public safety agencies. Upcoming webinars. Tomorrow, we're hosting a webinar on how to build and scale a drone program with Calvin. Calvin is the creator of the drone program at Cargill, and Cargill is one of the biggest companies in the world. They operate in 70 countries throughout the world. And we're also going to have a guy named James Manny, who heads up the UAS program at the Tennessee Valley Authority, talking about scaling a drone program. He just was added a little late. That's why he's not on this slide. And then next week, we have a webinar on drones and oil and gas with folks from Chevron. And finally, I think this might be especially of interest for those of you on this webinar. Next week, we also have a webinar on specific use cases for 3D modeling, talking about photogrammetry in action with Lori McBean as our guest speaker. So she's doing these things that we're talking about today on a daily basis. She's navigating the complexities of doing indoor 3D mapping. And then we'll also have Gregory from the Flyability team, professional services engineer, speaking about this similar topics and challenges that come up. So we hope to see you on some or all of these upcoming webinars. With that being said, let's dive into the Q&A. So the first question, this is a question that has come up quite a bit today. It's about accuracy, and I think, Andrew, I think this is for you, but Marc, you may want to jump in as well, because it's about accuracy in the Helios 2. So the question is, what accuracy can we expect in measurements on 3D models of indoor spaces that are obtained with the Helios 2?
Marc, I'll try to answer it unless you interrupt me.
All right,
so here
go
goes.
ahead.
Cool. So at least so I speak from Pix4D's perspective, and from our perspective, the accuracy of any measurement that you can achieve will ultimately be traced back to let's say, not the quality, but the original information that you used to reconstruct your scene in 3D space. And you can, one metric you can consider is, most importantly, and most often across all of your projects, is what we call the ground sampling distance of your images. And it's a metric that defines kind of like the real world, if you will, resolution of an image. And it's typically measured in centimeters per pixel. Now, if everything has been tied together correctly, because that's what Pix4D Mapper is trying to do when it's processing your photos, then we expect, under normal circumstances, that the accuracy of any measurement within the reconstruction will be accurate to within 1 to 3 times the average ground sampling distance of the images. Now, that assumes that the information you're using to scale and orient your reconstruction is as accurate, if not more accurate, than the ground sampling distance of your photos. But that's typically what is the rule that we apply when trying to estimate the accuracy of the project. The ultimate way to really determine it would be for you to run an empirical test in your own circumstances with your own camera with either check points or probably more often in the indoor environment, check dimensions, where you measure a handful of identifiable features using a tool that you have used successfully in the past and that you trust based on your own experience. And then you measure those same dimensions in your 3D reconstruction and you compare the results. And unfortunately, while I'm not certain of many things in my life, I'm confident that if you capture and process your data correctly, that the accuracy for any dimension that you pull will be on the order of centimeters, certainly not tens or hundreds of centimeters, generally speaking, for a typical project. I hope that answers the question.
I think it does, unless Marc, do you have anything that you'd like to add?
So just to add some information in the order of magnitude that the LEOS2 is able to achieve when you're at 30 centimeters from a surface that you're inspecting, you get a resolution of 0.18 millimeter per pixel, which is the ground sampling distance, basically. So this is the most precise degree you can actually capture data, but definitely there's no way you can get that kind of accuracy on a very, very large model like the one we've presented today.
All right, thanks so much, Andrew, and thanks so much, Marc. The next question, I think, Andrew, this is going to be for you, but Marc, I think you might have some experience with this as well, so I'll let you guys figure it out. But the question is, what is the workflow from data capture to a 3D model using the LEOS2?
Maybe I can comment on that. I think this is a question which comes often and which has other implications as well. So basically, the LEOS2 only captures a video stream. There's a possibility to mark point of interest, and when you do so, you extract a 12 megapixel image. But in general, you capture a video stream, and then using the inspector software, which is a piece of software we provide for free with every unit, there's a function where you can actually extract images every X amount of frames and create a database of frames, which then is your entry point for processing with photogrammetry software. In the process of the export, we tag every images in the metadata with information that is useful for Pix3D Mapper to detect which kind of drone has been used to build that model. And at the same time, we're also exporting a configuration file, which is useful or which is used by Pix3D Mapper to create the project and get started with processing. So that being said, once you have that export done, it's a two-click import that you have to do in Pix3D Mapper to get started with the processing of your project. But it also means that if you have the configuration, and if you're let's say courageous enough to go and configure another photogrammetry software, there is possibility also to use the outcome of an inspection with a different software. Now, we do have a partnership with Pix3D, which is providing a better solution altogether, very integrated. So this is why we're also together presenting with Pix3D today.
Thanks so much, Marc. And we just have a general question about the LEOS2. Can you speak to how the LEOS2 compares to other drone technology that's available on the market?
Yeah, well, that's a question that comes often when it comes to building 3D model, because there are other technologies on the market to especially we start to see drones that are embedding LiDAR and to build 3D model. Actually, the 3D models are quite different because one is only structural, the other one is visual. So you really have a chance to see you know, the colors and the features in the images. When in a LiDAR model, you don't see that information. But I think the most important difference between other technology and the LEOS2 is the ability of the LEOS2 to go in extremely tight space. and this is something that you won't be able to achieve with another drone technology. I was showing this ring where you had the refractory missing on it. So this is just a portion of a vertical pipe that is probably 50-meter high or something around that, and it has a diameter of 50 centimeters. So I mean, even this other technology would not even get inside the pipe, and we're not talking about flying safely up to the top and going down. So I think this is really one of the main difference, and I think again, you know, DLUS2 is a tool in your toolbox, and it doesn't mean that you don't have to combine it with other drone technologies to achieve a greater result when you're applying this technology to your industry.
Thanks, Marc. Andrew, I think this is going to be a question for you. Can you tie the relative accuracy of the generated point cloud to the absolute accuracy of the overall project area when required?
Okay, I hope I understand the question. I believe that they're interested in wondering whether or not it's possible to take, let's say, reconstruction that was reconstructed in relative space, and then, let's say, georeference it, align it, co-register it with a completely separate reconstruction that is georeferenced in absolute space, so we can actually get a sense of where we are on the planet. And the answer in a single word to that question is yes. The longer answer is you need more information, right? You'll need to be able to identify common points between the, let's say, real world reconstruction that is georeferenced in absolute space and the relative reconstruction that you've generated with ELIOS-2. And there are a couple ways to do that. You could, the one example that I have seen in an indoor environment like a mine was they had shot ground control points using a total station underneath, underground, obviously, and they used a handful of those shots that to georeference their results. And as soon as they did that, then because their reconstruction was georeferenced using the same set of ground control points that were defining the same coordinate system as the rest of the project area that had been reconstructed previously, everything was, even though they weren't connected to each other, they were by definition aligned correctly relative to each other because they used a common set of control. So that would be the most logical way to do it. I hope that answers the question.
I think so, yeah, and I really appreciate it, Andrew. I think we have time for one more question. One thing I want to say, one of the questions we had was, how can we access the data set with the STOPE that Andrew covered? That's in the chat pane, so if folks haven't seen that, we did put it into the chat pane, so go and look for the link, but it's there if you're interested in seeing the data set that Andrew was talking about. So this is the last question I think we're going to cover today. When using, and Andrew, this is going to be for you, when using our laser scanners, we use targets, that is spheres of a known size, that the software automatically detects when analyzing the scans. Is there a similar functionality that can help or aid in the photogrammetry with Pix4D?
The single answer is no, at least not in an automated way. Pix4D Mapper doesn't automatically recognize the let's say the standard dimension of let's say a known object like a sphere when you're working with point cloud data. So you would, under normal circumstances, do something similar to what I showed you earlier, where if you were able to identify those same points and you knew the distance between them, then you could use that to scale. But if you are also using those same points as ground control, then you could, you had a known position, not just a known size, but a known location for each of those, then you could use that to georeference. But it is still today a manual process. There is no automatic recognition of the relative scale, let's say, of those spheres like you have with the point cloud software. That'd be super cool.
Yeah, I like the idea. One last question. We have just maybe a few more minutes. Is one constraint, this is Andrew for you, is one constraint sufficient to scale and orient a 3D model?
It can be. I wish I could give you a definitive answer of yes or no. For some people it is. For some people it's not, depending on the variables that I mentioned earlier. If the variables to consider are, for example, the geographic size of the project area, relative to the size of the constraint, how accurate your results need to be, how clearly you can identify each of the points in your images. So my rule of thumb is that I will try to always incorporate at least 2 constraints. And if I can't incorporate 2 constraints, then I can at least have 2 known dimensions, and I use one to scale and the other one to then check how accurately the project has been scaled. But if I was, but there are people who will use 1 constraint because they're not even necessarily interested in centimeter grade. They just need a plus or minus 1, 10, hundreds, either meters or square meters measurement, depending on the question they're trying to answer, the problem they're trying to solve. So I wish I could answer everybody's question, after learning more about the project, but there's no way for me to make a single statement that applies to everybody today.
Right, and that makes a ton of sense, that your individual needs are going to drive the data that you need, right? Well, thanks so much, Andrew, and thank you, Marc, too. I also want to thank everyone who joined today. That's all the time we have, but I think this is the beginning of a conversation for a lot of us, not at all the end. You'll see on the slide that's up, the Q&A slide, the contact information for several of us here at Flyability and for Andrew as well. If you have more questions for Andrew, please email him. If you have questions about the Elios 1 or the Elios 2, or how we support 3D modeling through our partnership with Pix4D, please reach out to Marc or Alex or Johan. All of these emails, we're all happy to help. So please don't be shy. Please do be in touch. And please join us for those upcoming webinars, especially the one next week on specific use cases for 3D modeling. We do hope to see you again. And again, the recording of this webinar will be going out. So thanks, everyone. That's all we have for today. We really appreciate you joining.